I'll just quickly show you one logistical thing before Steven starts. So I saw most of you did what I teached in the pre-session video, which was forking the repository. But at this point, because we're updating the repository constantly, you will see that you have an option when you go to the repository that's called a sync fork. Right? I don't know if you have it there. You'll see that you have this sync fork option. And then every time we start the session, every morning, then what you can do on your own repository is go to this sync fork option, which will be in your own copy of the repository, and just do update branch. And what this would do is it would bring the latest version of the repository we're working on with Steven to your fork of that repository. That way you have the latest version of the slides, the latest version of the notebooks, and we're working on the same versions of everything. So I'll do that live in here. And you'll see that, boom, I get something that was updated 20 minutes ago. Working with the same. So it's always this option. And once you've done it, you get this type of message. Thank you.
All right, thanks, Yabra. Let me just get my, so I made a couple of small updates to the first lecture slides. So let me, actually, so before I jump in, does anybody have any questions from yesterday? All right, so one small change, and I'll try to remember I have a mic on today, so not shout to project my voice. Where is this? Oh yeah. All right, so I thought Yabra did a good job yesterday in the coding session, and hopefully you now have a a pipeline to start doing some analysis. It's not Yabra's fault, but as you got to the end of the notebook, some of these things get a little mind-numbing. So, do I drop numbers? How do I count for punctuation? Do I split contractions? Do I, make whatever of the 20 choices one has to make? And so there's a temptation to sort of say, I'm going to do something. I referee enough papers that I can tell what some people do is just take another paper that was published well and do exactly what that paper did. But the problem is that's sort of a self-confirming equilibrium because everyone is just copying other people who probably themselves didn't know what they were doing and went back to some paper. Now, none of this would matter if these choices were inconsequential, okay? But I briefly mentioned a paper yesterday during Yabra's session, which I thought is important enough to actually put a link to. So this is a paper published in a political science journal that explores whether these pre-processing choices matter for very much. And I think the conclusion is if you're doing supervised learning, which is a prediction task in which you have an objective label, these choices aren't that important. So if it turns out that it was important to split contractions, the ability of your model to predict labels is gonna place importance on the feature you created. But if the feature you created is just noisy, it'll be dropped. But with unsupervised learning, that's not the case. So unsupervised learning uses the correlation structure among the features themselves without any external data to discipline what's important. And so you can actually change the correlation structure in features by how you do your pre-processing pipeline. And so they have an R package which helps people assess the sensitivity of clustering algorithms to pre-processing choices and makes an argument for the need to explore these a little bit more fully. All right, so that's that. All right, so the last update in the first slides is at the very end, which I want to put in for completeness. So we discussed the estimation of this multinomial inverse regression model. And it's interesting because all of the, where's the chalk? all of these interesting objects that we obtain in this polarization paper are obtained through this conditional distribution, right? So conditional on being a Democrat or a Republican, I have different word choices, and that lets me make posterior updates on somebody's political party affiliation. But it doesn't let us do forecasting, right? I mean, ultimately, what if I have an out of sample document? D prime, and I want to predict, for example, what political party that came from using speech. So I actually want to go back and do what's called the forward regression. All right, so the forward regression is what we're all used to in normal econometrics. I actually want to take the covariates and predict the outcome, not do this inverse regression. So there's a in this literature in statistics, there are results on how do I invert the inverse relationship to go back to the forward regression. And by the way, I also included this figure because it came up in somebody's question. I think Theo asked this. Oh yeah, there you are. So I basically drew this on the whiteboard at some point yesterday, but this shows how these posterior beliefs evolve in the number of phrases. Okay, so in fact, it's a little bit more dramatic than I had remembered, because once you hear someone speak 100 phrases in the period 2007 to 2008, you're already pretty close to inferring their true political party. Okay, and this previous, the very beginning of the sample, it's flat, more or less flat. Anyway, back to the point. How do I do this forward regression? Well, there's a nice result. This is not in the Ginskau-Shapiro TADDI paper. This is in the TADDI 2015 paper in the Annals of Applied Statistics on the formation of something called a sufficient reduction projection. So once I estimate my multinomial logistic regression model, I estimate a set of regression coefficients for every term and every covariate. Now let's say I want to summarize all of the relevant information in the high dimensional text data relevant for predicting covariate J. Right? So just to be clear, this data lives in a 7,000 dimensional space. And there's a remarkable result that I can collapse all 7,000 dimensions into a single scalar called a sufficient reduction projection by linearly combining the frequency counts of terms by the estimated regression coefficients on this J feature. So that scalar value associated with covariate J is sufficient for doing this forward regression. So you can basically drop all of the term counts, replace it by this sufficient reduction projection, and use that for this forward regression model. All right, so I'm not quite sure what model to specify. So once I've basically said I can model YD as a function of this ZD, I don't know the exact functional form that I would use for this. Like I could use a linear regression or include a polynomial term or whatever. It doesn't tell me what model to use, but it does tell me it's without loss of generality, if the model's true, to replace XD with this scalar. Okay, so that's a very nice result. The other nice thing you can do with it is carry around the ZD as a low dimensional representation of a document to go, explore whatever you might want to explore. So I have a paper with a couple of co-authors where we do this exercise for 10K files and basically use this ZD as some summary statistic of what a firm is, and then go plug that into regression growth panel models or whatnot. Okay, but I just wanted to quickly share this result for you in case any of you were wondering, how do I go from the inverse regression to the forward regression? Okay.
This last result, does it have to do anything with the, it's enough to control for propensity score and we can ignore the controls, or it happens to some similar but it has nothing to do?
So propensity scores are the probability that you are, so can you remind me in this context what you mean by propensity scores?
If I Like if I have a causal model and I care about treatment and outcome, and there's confounders, you want to have, you know, the propensity score is the probability that the treatment is one, conditional on X, your controls. And usually you want to carry around all the controls, and you want the outcome under control and the outcome under treatment to be independent of treatment, conditional on all the controls. And you have to deal with all the controls, and if you have many controls, it's a mess. So there's this cool result that says, oh, you don't have to deal with all the controls. It's enough to—
You just replace them with the, probabilities?
You just need to have the propensity score. And
Okay, so if what you mean by propensity score is, you know, it's an actual probability, right? So
yes,
you have,
probability of treatment.
Yeah, so I guess the only difference is this ZD is not necessarily a probability, but it tells me the information I need to carry around to estimate the probability. So I guess the analogy would be you have this, you know, high dimensional set of things that might influence the propensity score, and I'm going to somehow build an inverse regression model to, you know, account for how those individual covariates change in some variable. I guess this would be the treatment. And then you could basically linearly combine all of the covariates with their estimated regression coefficient on the treatment. And that would be a sufficient, well, it's not a sufficient statistic because it depends on data, but that would be the scalar object you would take out of sample to model other observations, probability of being treated. I think that would be the closest analogy here.
It seems to be related to linear discriminant, linear discriminant analysis and going from the logic to a linear discriminant analysis to a logic specification, where you model distribution of X conditional on the discrete objects, and then you can actually flip things around, and you can actually get a logic specification.
So for discrete models, I guess you can just use Bayes' rule to do the inversion. Yeah. Yeah. So the problem here is it's much harder to do Bayesian inversion when you have a continuous Y, and in fact you'll see that this admits multiple Y's, right? So you're actually just inverting this kind of, you know, marginal covariate, still controlling for everything else. But exactly, it's the same way.
But the one thing that, so you're essentially, if I understand correctly, you're specifying the distribution of X conditional on Y, and then you have a model for Y conditional on Z or X. Is it obvious that these two conditionally specified distributions have a well-defined joint?
Yeah. So let me go kind of more slowly, make sure I don't make any mistakes. The joint can be built from the inverse regression by specifying a probability model for the outcome, which I guess is easy in the sense that it's just you know, a standard numeric covariate. So call it whatever you want to call it.
Yeah. So ideally, you would want to get the what do you call the Y on X one, the direct regression.
Right.
You would want to specify that out of what this reminds me of, there are results in statistics and probability that you can have condition specified models where I specify X conditional on Y and Y conditional on X. Sometimes you have more than one joint distribution.
I see. Yeah, no, I hadn't thought about that. So certainly we have a model for this from our inverse regression. We also have a model for this.
So the question is
whether these are kind of one-to-one mapping.
Yes, if this gives you consistent equations or, you know, a unique solution to the joint. Things like that.
That's a good question. Yeah, I haven't fully thought through that. Yeah.
I have some references that they go back to the Markov chain literature, actually. Because you can think about this as a Markov chain.
Yeah.
Whether you have a unique invariant distribution and things like that.
Okay.
We can talk about that.
Yeah, please send it.
This is the detail.
Sure, okay. So where did we end up yesterday? So we ended here.
Anyways.
Remember the structure of this factor model, changing tack completely and moving away from modeling the distribution of XD directly to modeling it in two stages, where first a document has some factor loadings called theta, or topic shares theta, and then XD arises from a beta distribution conditional on the topic allocation. The key parameters of this model were a set of multinomial distributions over vocabulary space described by beta vectors, each one of which lies in the V-1 simplex. And then we had a set of document level topic shares that lie in the K-1 simplex. We have a likelihood function. And now we want to do inference on these parameters, right? That's where we ended up yesterday. And then we said, well, let's think about our document term matrix as being normalized. So the document term matrix really turns into a document term frequency or term proportion matrix. So let's say my original document term matrix were 1, 3, 0, 1. 2, 0, 1, 1. What we're saying is I'm going to convert that into a matrix of shares, right? So I'm just going to row normalize everything. So this is going to be 1 plus 3 plus 1 is 5. So it's going to be 1/5, 3/5, 0, 1/5. And this row is going to be 1/2, 0, 1/4, 1/4. So I'm talking about now a share space. Well, this structure, this factor structure, tells me what the model-based share should be, right? So what's the model-based share of the first term in document 1? Well, it's going to be the sum over all the possible topic assignments of that first term in this document. A document-specific weight on each one of those K topics. And then what's the probability that each one of those K topics would have produced the first term? That's the model-based share. This is the empirical share. Somebody showed, Ding and his co-author showed, that the maximum likelihood estimates for theta and beta are equivalent to matching or trying to match the empirical share with the model-based share. So I'm going to go element by element, right? So that would be the first term in document 1, the second term in document 1, so on. I'm going to go element by element and try to match each cell in the matrix with the model-based predicted share. And lo and behold, you can think of that as a matrix operation, right? Because if I matrix multiply this row stochastic theta and row stochastic B matrix, I will exactly have tried to match the empirical moments with the theoretical moments. So this is called a non-negative matrix factorization, right? So if you go to R or Python and search for, like probably scikit-learn, we'll have a non-negative matrix factorization package. You would take the document term matrix that Yabra showed you yesterday. You would scale that X matrix so that every row was divided by its length. And in one line, you'd say, compute the non-negative matrix factorization for this X prime, and bam, you've solved this probabilistically in semantic analysis model. Okay? Just a little bit of history.
Is this factorization unique?
No. But let's talk about this first. I did promise to make some connection to non-textual data. So let me move these controls out of the way. So you told me I could do more hide float meeting controls, and then I'm going to make sure to click again. I can do this. Great. Okay. So as far as I can tell, the non-negative matrix factorization was first introduced in the literature. I think that's either a Nature or a Science paper. And one of the first examples was in image processing. Okay, so to be fair to the literature, this did not start with text binding, it started with images. And this is a bag of visual words image model in which faces, so you can see there's, this is our face data, has been represented by 19 by 19 pixel grid. And every pixel in the pixel grid is shaded black-white on a 0-1 scale. So if I unfold every image, it's going to be a 19 times 19 length vector whose elements are between 0 and 1, and that's going to represent a face. Okay? So you can do principal components analysis on this set of images in this file, and that would be equivalent to latent semantic analysis in text mining. And these are the underlying factors. Okay? So you can kind of see there's an original face here is one of the factors. So that's, a kind of canonical face. And then the black indicates positive real numbers and the red indicates negative real numbers. So the interpretation is when you do a principal components analysis, you start with sort of a generic face, and then you start adding and subtracting variance on human faces. Okay? And then this is the set of loadings that are specific to this original image, and from there you reconstruct the face. Now, a non-negative matrix factorization has a very different representation of how you build a face. So you can see here that rather than start with a standard face and then adding and subtracting kind of face templates, you actually start having face components. Like these would be eyelashes. There might be a mouth. That's some kind of like eyes, whatever. Okay. And then that gets linearly combined to form a face. So it's not so much that the two faces look different, it's that the underlying factors look very different because the structure of the matrices that you're factoring are different. Okay. The point being that this is a more, interpretable space in the sense that you get the low dimensional representation that's sort of modular rather than just moving around in some averages. Okay? So we'll see how this works in text data in a minute, but let's come back to the question. I think someone here asked it, I forget who, about whether this factorization is open. All right, so there's a nice paper by Kay and Monticello Lea and Nesbitt, I think is the other author, on this problem, on the non-uniqueness of non-negative matrix factorizations. And I think there's a nice intuition here. This image is from their paper. So let's start with a V equals 3. So there's a 3-dimensional vocabulary space. So remember, in this 3-dimensional vocabulary space, we're going to be operating in the 2D simplex. So this comes straight from the precessional materials if you watch them. So the 2D simplex in a 3D space. So that's going to be the point of the simplex where the second term has all probability. That's the corner where the first term has all the probability. That's the term where the third term has all the probability. And how do I build up my representation of documents in the simplex with a non-negative matrix factorization? Well, first I'm going to locate my beta vectors somewhere. So the beta vectors live in this V-1 simplex, and they live somewhere. Okay? So let's say that beta 1 is there. So that defines a distribution over these 3 vocabulary terms where most of the weight is on the first and the second terms. The beta 2 is another distribution over the vocabulary space that puts most of its weight on the third and the second terms. And now every document has to be a linear combination of those 2 betas. Okay? So let's say theta d is 1/2. All right, well, if theta d is 1/2, it's going to lie just between beta 1 and beta 2. Well, I didn't specify which element. So that if the theta d is 1/2, it's going to lie in the middle. If the theta d is 1/4, 3/4, it's going to lie somewhere down there. Okay, so every one of these documents is going to be a convex combination of beta 1 and beta 2, and how close I am to beta 1 is going to be determined by my theta vector. All right, now that's just one representation of this system. How could I generate an equivalent representation? Well, I could move beta 1 a little bit up the red line. I could move beta 2 a little bit down the red line. And I could, again, regenerate every document using some new set of thetas. Okay? So the answer to the question is this non-negative matrix factorization is not unique. Therefore, following Ding's results, the maximum likelihood estimates are not unique. So what should we do? Well, if you're doing machine learning, I'll show you what machine learning people do. Econometricians don't, at least, well, I'll get into this discussion in a minute. But without, staying in this frequentist estimation framework, is there anything I can do to ensure identification, to ensure there's a unique factorization? Can you stare at this figure long enough and see whether there's a clever defensible way of having a unique beta 1, beta 2, and thetas? Yes. So that's the idea of having anchor words. So if you Google topic model anchor words, you'll see I'm not discussing it here because it's a bit niche, but if you're willing to assume that every beta has a term that only appears in that beta, then you can uniquely factorize the document term frequency matrix into a theta and a beta. Okay, so basically there is a B prime such that a K prime exists where beta K prime V prime is bigger than 0. Okay, so there is a topic where this term is positive and beta K V prime equals 0 for all K not equal to K prime. So that term never shows up in any other topic. Why does that work? Well, that's exactly basically saying I'm going to slide the beta 1 to the edge of the simplex. Okay, so that would be term, so if I slide beta 1 there and I slide beta 2 there, each one has a term that never appears in it but does appear in the other. Okay, so this is a more general result. And once I have a beta 1 there and a beta 2 there, there's now a unique theta that would rebuild every document. And so I would achieve this unique factorization. Okay. So if you want to stay in the world of frequentist estimation of these factor models, and you care about point identification rather than set identification, you can explore this anchor word idea. Okay. I was at an econometric seminar in Chicago last week, and Jose Montiel Olea was presenting a second paper in which he was exploring this anchor word idea. Okay. What has the machine learning literature done to overcome this problem? Well, they have extended the factor model to incorporate some prior distributions over the thetas and the betas. And so if you put a prior distribution on these thetas and the betas, for those of you who watch the pre-sessional materials, there is a motivation to choose a conjugate prior so that Bayesian computations are simplified. And the conjugate prior for multinomial distributions is the Dirichlet distribution. And so the natural choice for computational ease would be to throw a Dirichlet distribution over the theta d's, a Dirichlet distribution over the beta k's, and that model is called latent Dirichlet allocation. Okay, so it takes the probabilistic latent semantic analysis model of Hoffman, gives it a Bayesian, Bayesian interpretation, and that's called LDD. And that's become an extremely influential model in machine learning. And it, you could argue it's a bit outdated by now in the NLP literature, which has gone in the direction of deep learning. But it's still a very interesting, for those of you who find it satisfying to write down a tractable probability model over a high dimensional space, it's a very elegant solution. Now, before we get into the applications of this, let me have a little bit of a philosophical discussion that you may or may not care about. For reasons that are not entirely clear to me, econometricians seem very skeptical of Bayesian methods. So one of the criticisms in this K paper is that, at least asymptotically, we would like the prior distribution over my model parameters to not matter for the parameter estimates. Okay, so maybe in small samples, it's all right for prior distributions to have some influence on my estimation, but asymptotically, that shouldn't happen. I think there's a literature on Bayesian robustness that discusses this point. Now, because of the non-uniqueness of the non-negative matrix factorization, that's not going to be true in this model. So depending on the specific Dirichlet distribution you put on the betas and the thetas, it is going to influence, even asymptotically, the estimates that you form for the thetas and the betas. And some econometricians don't like that at all. All right, so the proposed solution in this paper is to just keep recomputing non-negative matrix factorizations. All right, so let's not worry about point identification. Let's do set identification, and let's estimate the identified set through just repeated computations of the non-negative matrix factorization. And that's going to be all I can say about what betas and thetas are consistent with my underlying data. I think that there is an argument for there being more reasonable factorizations than others, and I'm happy to put more weight on that in the following sense. Let's think about these betas. These are distributions over vocabularies. In natural language, as we saw in the first slide, those distributions are skewed. Okay, so Zipf's law applies for natural language. I am therefore comfortable with models in which the betas are skewed. All right, so the betas are near the corners of the simplex. So if a non-negative matrix factorization has betas that are roughly uniform, I don't view that as a reasonable model of how term frequencies look in natural language conditional on talking about something, okay? So how would this translate into the model? Well, you would choose the Dirichlet hyperparameter on the betas to have a small eta, which would put more weight on sparse betas in the posterior. And yes, you're going to carry around that assumption even asymptotically, but I think that's a reasonable assumption to make about the structure of a language model. All right. Ultimately, different people have different opinions. Econometricians sometimes don't like putting these assumptions and these structures on models, and they just want they want to know what the data can tell you and no more than that. They don't want it to be combined with your assumptions about the model. But anyway, I'm not here to resolve this. I'm just here to alert you to the fact that it's not innocuous to put prior distributions on this model space. Okay, you're saying something substantive about what your estimates are going to look like, even asymptotic.
Stephen.
Yeah.
I'm not going to defend the competition.
Okay.
I want. Could you also do empirical Bayes? Estimate the eta and the alpha.
Yes. Yes, you could. Yes. So there's so I think there's a paper by Hannah Wallach that does that. Yeah. So in the applied literature, what tends to happen is people specify an alpha, which is sort of non-controversial. So you could have a uniform alpha, for example. Sorry, a uniform Dirichlet induced by alpha equals 1, and then like a small eta like 0.01. And just go with that. Okay. So just to come back to this point, the original paper, so if you read the Bly, Jordan, and Ng 2003 paper, the Dirichlet, in fact, is only placed on the thetas. So the betas are actually maximized in the likelihood. Okay. All right. So as I said, why would I want to do this Bayesian approach? Well, one is, in these high dimensional models, regularization is needed, and so you can always interpret these priors as a form of regularization, or this weak identification problem of the non-negative matrix factorization. It basically gives you a way of selecting the more reasonable elements of the set. Okay, so whatever. Now this is, I would say, the most popular probabilistic model for text. There are many variants. We'll explore some later in the slides. It's also shown up in a few other contexts. So it's a core model in population genetics. So from what I understand, gene data is also high dimensional and discrete. So it's been so long since I've done biology. I think DNA is built from 4 letters, like T is one of them, and there's a few other letters, but basically genes are long sequences of 4-letter combinations. And a gene pool, like a European gene pool or an African gene pool, is going to be a distribution over that high dimensional discrete space. And Stephen Hansen is built as a convex combination of different gene pools. Okay, so my dad was from Denmark, so there's some European thing. I think one grandfather was from Lithuania, so there may be more Asian, genes in Eastern Europe, and so I'm going to be some convex combination of these things. Okay. And we'll also see a similar idea applies in survey data and network data and so on. All right. So in some sense, this is a generic way of factoring a high-dimensional discrete data model. All right. So how would this work? Let's go back to our FOMC running example. And this is a particular data point in the FOMC transcripts. So let me read it out. We have noticed a change in the relationship between the core CPI and the chain core CPI, which suggested to us that maybe something is going on relating to substitution bias at the upper level of the index. You focused on the non-market component of the PCE, and I wondered if something unusual might be happening with the core CPI relative to other measures. All right, that's a little bit of a mouthful. And let's see how we would factorize this thing using this, theta beta language. So first, as Yabra discussed yesterday, we need to start pre-processing this data. So we're going to remove stop words. We're going to stim. At this point, this is a bag of words model. So you could arbitrarily scramble any of these words together and represent this document as just term frequencies over the remaining terms. Okay. Now, this is real data, real estimates. This is the posterior distribution over the theta that characterizes this particular statement. This is a 50 topic model. By the way, I told you where the alpha and the eta come from. What's the third thing you need to write down to estimate the model? You need to estimate the K. I haven't told you about that yet, but now I imposed K equals 50. And the mode of the posterior is quite distinct and located on this 25th latent dimension. Now, what is the 25th latent dimension? It's a probability distribution over a vocabulary space called beta 25. That is a visual representation of beta 25, where the size of the element in this word cloud is roughly proportional to its probability in beta 25. And there's one kind of standout stim in this beta distribution. It's the stim for inflation and related words. And then, there's other terms, level, CPI, percent higher, and then a vanishing smaller probability term set. Okay. Now, the interesting thing about the example is how often does the word inflation show up in this text? 0 times. All right, so when you do these factorizations, remember what we're doing is we're constructing a latent representation of this document and ignoring the particular term counts. All right, so obviously what's going on here is that there's some latent topic called an inflation topic, and that induces a probability distribution over term counts. And so that generates co-occurrences conditional on talking about inflation. So in some other documents in this same data set, we see people using the word, CPI, which stands for Consumer Price Index, PCE, which is personal consumption expenditure, along with the word inflation. So whenever I see all these things co-occurring together regularly, that tells me that there's sort of a common factor that draws those terms together, so that even if I don't see the word inflation in this particular document, I'm going to infer that it has high likelihood because I see terms that regularly co-occur with inflation in this particular document, right? So if you were to use a dictionary method, going back to the models that we were talking about yesterday, what's the, if I wanted to create an inflation index from a dictionary, what's the one word I would include in it? Inflation, right? That would totally miss this example. Okay, so that's the advantage of working in a latent space where you kind of endogenously learn, the correct representation for topics rather than impose it from above on these, with these term counts.
So excuse me, so it learned it just by the data we gave it?
That's right. Yeah, so this is pure unsupervised learning. There's no, there's always a human need to attach some label to this, so you could call this topic 25 dash in quotations inflation, but that would be a purely subjective exercise because no label went into this, okay? If you wanted to use this anchor word idea that I briefly discussed, that might be a path to more supervision, right? Because I could have I could assume that there's a topic called an inflation topic, which has the property inflation only shows up in that topic and nowhere else. So now because I've kind of imposed that, I know a little bit more about the factor structure I've generated. But this has no human input, except for alpha, eta, and k. Yeah.
Sorry, just to clarify, if we decide to go through that way of choosing the metas, in which every factor has a particular word that only appears in that factor, do we need to impose which word it is, or it would be?
No, so
I just impose that characteristic.
yeah, so if you impose this characteristic and you want to compute a non-negative matrix factorization, there are algorithms that, so there's a little bit of a question about whether such a set of anchor words exists, but there are algorithms that go look for those anchor words and then provide you the non-negative matrix factorization. Another approach would be to impose them yourself and then ask whether or not your imposed anchor words are consistent with the non-negative matrix factorization. But in the literature that I've seen in machine learning, the anchor words are learned by an algorithm, not imposed by a researcher.
Could it be that there are multiple sets of anchor words such that there's a solution? Because then even doing that, it could be the case that it's not unique.
So I guess I believe the statement is, given a set of anchor words that satisfy this property, there exists a unique non-negative matrix factorization. We don't know whether such a set of anchor words exists, and I don't know whether such a set of anchor words is unique, conditional, on existing.
Thank you.
If we have some prior that, there's 3 topics, inflation, growth, and recession, can we just simply
Yeah, so one less extreme way of having this anchor word seed word idea would be to encode those beliefs in the, directly in the prior distributions. So these Dirichlet distributions are all symmetric, but you could, have k equals 3, and then specify your Dirichlet prior over topic 1, such that inflation, CPI, and core have relatively high probability. And in topic 2, another set of words have relatively high probability, and so on. And then that prior assumption is going to percolate down into whatever posterior distribution you estimate over the system. All right, so if you're gonna estimate one of these topic models, it's important to at least try to validate them. There's a certain subjectivity in staring at these word clouds and claiming that they mean something. So following on from the previous estimate of a topic model, this now is the same data set, this FOMC data set, but taking the estimated model and representing meeting level topic shares. So every meeting is a decomposition into a set of topic shares that sum to 1, and I'm pulling out specific parts of that meeting level share vector. Right, so the black series is the meeting level share of the 35th element of this factor space, which has this word cloud. And this chart shows the meeting level share of topic 12, which has this word cloud. So it's tempting to view this as a topic that captures discussions of risk and uncertainty, and this topic that captures fiscal policy, with the awkwardness that will is a bit, what does that mean? And, all these interpretations of topic models are a little bit, I don't know how you would say, subjective or subject to noise. But if you want to convince people that this factor structure actually captured something meaningful, you need to spend some time externally validating, and these meeting level topic shares are here plotted against the Baker-Bloom and Davis uncertainty index, which is meant to be about policy uncertainty, fiscal policy uncertainty. So you see that these things do co-move. It's not perfect, but it gives us some sense that this is reflecting something real in people's language, not some artifact of a high dimensional correlation thing that doesn't relate to reality. Okay. Is there some other question? All right, so other ideas for validating a topics model output. So you can rank each of these 50 topics in terms of which ones are more discussed in recessions relative to expansions. Right, so these are the 2 topics that are most discussed in expansions relative to recessions. And the content of these looks reasonable, okay, to the extent that when we're in expansionary cycle, we'd be talking about growth and increasing productivity. These are the two topics that are most discussed during recessions, and you see one of them includes the word recession and economic weakness, and two of the three recessions in the sample period were induced by financial crises, and so it's natural to talk about the banking sector. The point being, if you estimate a topic model, and we talked about concept detection as one of the 4 core problems in this space, it's very tempting to say this is automatic concept detection. But you need to do a bit more than just print a word cloud and say, of course, this means that they're discussing risk and uncertainty. You need to do efforts to sort of convince the reader that you've learned what you want to learn. Let me go through one more example, just to convince you that this same technology works across multiple domains. So this is a set of newspaper articles drawn from the New York Times that contain the words Iraq, Iran, and Syria in their headlines from the mid-1980s to whenever I estimated this on my computer a few years ago. These are the estimated betas, so I'm not putting word clouds. So I think this was a k=20 model. And these words are ordered in terms of their probability in these particular betas. So American is the most likely term in topic 0, and force is the second most likely term in topic 0, and so on. These are the year level shares devoted to these different betas, right? So these are the theta vectors that correspond to the different betas across the sample period 1980 to 2015. And again, you can see that this seems to co-vary with some external reality. So what's topic 7? Well, it includes Iraq, Iraqi Hussein, Baghdad war, whatever, Kuwait. And in the early 1990s, where this green curve peaks, Iraq invaded Kuwait, I think in 1990, 1991, okay? Well, following the Iraqi invasion of Kuwait, there was some military intervention by the US and other countries. Weapons inspection was put in place. They tried to disarm Iraq. So you see this topic 9 contains various words related to, chemical weapons inspections and probably, United Nations programs and whatever. And then September 11, 2001 happened, and somehow the US ended up back in Iraq, okay? And if you look at this topic 0, we've already seen that that contains words related to American military forces. All right, so, all of this, of course, is descriptive. I'm not here to claim that we're doing science or that we're doing econometrics. But I am showing that in different domains, this idea of modeling the factor structure in text does 2 things. It produces a relatively interpretable set of beta distributions that lets me start to understand what my textual corpus contains. And it gives me a set of thetas that let me understand document level heterogeneity. All right, and then the main idea in empirical strategies that use topic models is to take these document level thetas and explore interesting ways in which observations are different in the data according to other observables. Yeah?
Just to understand a little bit how to interpret graphs like this green curve. Basically, the first war on Iraq finished in 91.
Yeah.
I see basically here that pretty much it looks like the interest remains stable between years 91 and 2000. That's before September. Was it really the case?
So we're talking about
after 91, there's just like a marginal drop, right? At least that's eyeball econometrics, but that's what it seems to me.
So are we talking about this topic 7?
Yeah. Topic 7 was about Iraq war.
Yeah, so it just includes these like Iraq, Iraqi, Hussein, Baghdad war, Saddam, Kuwait.
So war finishes in 91, but the curve indicates that there's kind of a stable interest.
Yeah, I mean, so all these things are a bit imperfect. So yeah, exactly. So I was just identifying the mode, but you're right. There's a second mode that's exactly 3 or 4 years later, and in some sense, this is a little bit generic, right? This Iraq, Iraqi, Saddam. It's only when you get to this word Kuwait that it sort of suggests that this would have anything to do with Kuwait. So, there's going to be some generic text, I guess, in the 90s that's generically discussing Saddam Hussein and Iraq. And whenever you see that, it's going to have some weight put on topic 7. So none of this is like a, I don't want to think about this as a perfect partition or.
Yeah, it's just my
Yeah.
prior was that in the war year, there would be much higher interest
Right.
compared to the next years. That's was my.
Yeah.
Anyways.
I mean, I'm glad you asked these questions because all of these exercises are a little bit ad hoc and, I can provide these post hoc rationalizations, but it's all a little bit iffy, okay? But that doesn't mean it's not useful to plug in these things into regression models. And I'll show you a follow-on example of this later in the slides. I don't know what people's, yep.
There are also some methods for empiric evaluation of these LEA methods, such as the perplexity score. Do you think they are useful, or what's your take on that?
So can you elaborate on what you mean by perplexity score?
It's basically capturing how surprised the model is to see new data, and it's sometimes used in papers who apply these LEA methods.
Right.
And I was wondering if it's useful to maybe, I don't know, show in papers if you use LEA, or if it's better or nicer to show the external validity of like.
Yeah. So let me jump one slide to this, which I think speaks a little bit to your question, and revisits the idea of model selection K. And in revisiting this idea of choosing K, asks the question, how should I evaluate these topic models and why do I write them down? Right? So from a traditional statistics or machine learning perspective, what would I do to evaluate a topic model? Well, I would evaluate them at some task that I believe is important. So if I do machine learning, I would evaluate the out of sample properties of my model. So this is the context in which I've seen perplexity scores is, all right, so I take some training data, like I draw 2/3 of the New York Times articles, I estimate LDA on it, and now I ask, to what extent do my betas explain the variation in this held out sample? Okay, and typically the perplexity is used, which is a monotone transformation of the out of sample log likelihood. Okay, so that would be a machine learning answer. A statistics answer would use an information criteria. Okay, so some trade-off between model complexity and goodness of fit. And there's some ideas about how you do information criteria in topic models. Now, in some sense, if you want to do eyeball econometrics, which is what Theo was suggesting, or what a lot of people implicitly do, I'm just going to stare at things and convince myself that they mean something. You might think about formalizing eyeball econometrics. Okay, and this is, I think, in the literature, my favorite way of evaluating whether topic models are internally consistent. So there's a paper in NIPS from, I don't know, 10 or 15 years ago. Oh, sorry, 15 years ago. Asking, can humans interpret topic models? And how does humans' ability to interpret topic models depend on K? All right, so the important question is, if I chose K based on statistical first principles, would I be aiding people's ability to actually interpret data? Right? So they use Amazon Mechanical Turk and perform 2 tests of humans' ability to interpret topic models. So the first is a word intrusion task. So I'm going to take betas, all right, so let's say these lists from my estimated topic model, and I'm going to present people the first 5 words of the list, so American Force Military Troop Command, and now I'm just going to randomly insert a 6th word from my vocabulary. Tell me what the randomly inserted word is. The idea is, if you've written down an interpretable topic model, the randomly inserted word is going to be a clear outlier unrelated to the top 5 words in the beta. Okay, so that's called a word intrusion task. There's also a topic intrusion task where I show people a snippet of a news article. I show them the top 3 topics associated to it in terms of the beta distributions. And then I'm going to randomly draw another beta distribution and ask, what's the topic that doesn't belong in this article? And then I'm going to ask, how does people's ability to perform these outlier detection tasks vary in the size of the model? Okay. So this exercise is done for K equals 50, K equals 100, K equals 150 for New York Times and Wikipedia articles. Here's a graph of the main results. Sorry that the print is so tiny. So this is the predictive log likelihood, which is, as I said, a monotonic transformation of perplexity. And this vertical scale, although it's not labeled, measures human success in conducting these topic and word intrusion tasks. You see that these lines are either flat or negative, which shows, or is meant to show, that there's a negative relationship between the out of sample goodness of fit machine learning style model selection and model selection based on maximizing interpretability or cohesion, right? Now, presumably, most of us write down topic models as an initial exploratory analysis of a large unstructured data set. Not many of us are writing recommendation systems, right? So if your goal is to maximize interpretability, doing something like this is arguably better than the standard things that would be your first instinct. But now the question is, no one wants to go on Amazon Mechanical Turk every time you write a research paper. So is there any way of like automating the process of topic evaluation? And again, there's a small literature on topic cohesion. This is the one paper I'm aware of. I put a citation in here that maximizes the point-wise mutual information of the estimated model for different values of K. So what this boils down to is choose different values of K and then ask how often do the top terms in the beta distributions co-occur in sentences in English. Okay? So you basically want to have word clusters that tend to actually interrelate in English texts. Okay, the formalization of this idea is called point-wise mutual information, but there's a kind of automated way of doing this topic evaluation. Okay, I'm not sure if that answers the question, but this is a way of sort of thinking about how to evaluate whether topic models are good at the task we've designed them for, and typically in social science, which is maximizing interpretability. Okay. Now we're almost done with our first hour. Maybe I can take a poll. We could spend 2 hours talking about Bayesian approximation. I've just shown you a lot of betas and thetas. Somebody might have asked, where did these things come from? They came from Bayesian computations. I'm never sure where to strike the balance between just ignoring all of this entirely and giving, a course in Bayesian approximation. The estimates that I showed you were the result of something called a Gibbs sampler. I don't know. You guys know what a Gibbs sampler is? No? Do you care what a Gibbs sampler is? Half of people do, half of people don't. Maybe I'll spend 3 minutes telling you what a Gibbs sampler is, so you get some rough intuition about how these numbers were produced. I mean, in practice, of course, I'll show you a notebook. Stick the document term matrix into a Python function, provide it alpha, eta, and k, and push click. I mean, that's what most applied researchers do, but you might care, what's being done. So let's say that I have a joint distribution over variables x1 and x2. And I want to compute this joint distribution. A posterior distribution, for example, is a joint distribution. And it's got some complex, intractable shape so that I can't write it down. Okay? So Markov chain Monte Carlo methods are a way of drawing samples from this complex distribution, right? So the first approach, and probably the most well-known approach in econometrics for doing a posterior inference, approximate posterior inference, is this MCMC method. Okay, and Gibbs sampling is a particular kind of Markov chain Monte Carlo algorithm. So you basically assume that you can compute conditional distributions. So I can compute the conditional of x1 given x2, and I can compute the conditional of x2 given x1. And this is true in LDA because of the Dirichlet multinomial conjugacy. You can actually compute these conditionals. All right, so I'm going to randomly initialize my algorithm in some space. And then I'm just going to iteratively draw samples from these conditional distributions. All right, so I'm going to start by fixing x2. All right, so let's fix x2 at its initial place. And, that fixes Okay, sorry. X is x2, exactly. And now I want to draw a new value for x1 from the conditional distribution x1 given x2 equals whatever fixed point that I've chosen here. All right, so that was my initial draw of x2. So I'm going to take a new draw of x1 given x2 equals x2, 0. And the important point is that is a closed form distribution that you can analytically characterize and sample from. Now, on average, your samples are going to be drawn from where the posterior distribution has more mass. All right, so even though the joint distribution is ugly, this conditional distribution you see is going to have a nice kind of unimodal shape. And I'm going to take a new draw for x1. That's going to be x1, 1. Now I'm going to do the opposite. I'm going to fix x1 and take a draw for x2 using that conditional. And again, that's going to be a nice unimodal distribution. And I'm going to take some new draw for x2, and that's going to be x2, 1. Repeat, 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 repeat thousands of times and just collect these samples. Okay? Eventually, once you collect enough samples from this repeated sampling of these conditional distributions, you're going to be sampling from the entire joint distribution. And you can collect those samples and start forming moment estimates like the mean or the variance or whatever. And that's what underlies the numbers that I just showed you. Okay, this Gibbs sampling approach. Right? In the original paper, they do something slightly more involved, which is called variational inference, which does not stochastically approximate the true posterior, but views Bayesian approximation as an optimization problem. So you consider a simple, like a simplified set of posterior distributions and try to find the element in the simplified set that's closest to the true posterior. So it's Bayesian approximation as an optimization algorithm, basically. Okay, that's less familiar to economists. So that's why these MCMC methods are sort of more easily explainable. And if you can use MCMC for a topic model, it's probably better because there are more statistical guarantees for MCMC algorithms as well, and whatnot. Okay, but anyway, that's the rough idea about how we've taken samples from the posterior distribution in this factor model. Okay, and it's actually not that complicated to write down these conditionals. So if we were doing a full 2-month data science class, even at master's level, I think it would be fair to ask you to code that from scratch. Okay, and I ask people to code it from scratch. Anyway, that's our first hour done, and we go get a coffee now. Okay.
Ya que vas a hacer algo
All right. Not sure if everyone is back, but I will start again. Just give maybe one word of warning. It's fine to not care about the deep theoretical properties of MCMC algorithms, or even how to code them yourself. But I sometimes think it's dangerous to have no knowledge whatsoever, because then you can make basic mistakes. Like, for example, one of the Python packages for implementing LDA via a GIB sampler, I think defaults to returning you the last sample that was drawn from the Markov chain. But that's like doing a Monte Carlo simulation with one draw. I guess it's unbiased on average, but sort of makes no sense. I mean, the whole point of doing Monte Carlo simulation is to draw thousands of samples from a distribution that go into your estimates of the average. Okay, so that's like one basic example. Okay, so you would want to modify the default behavior of a Python package that only returns to you the last draw to return to you the last 1,000 draws. And then you would form your thetas based on the average theta from all those individual draws. Another issue, for example, is that the initial draws from a Markov chain are not representative of the joint distribution because they've been arbitrarily chosen. So there's something called a burn-in period in MCMC estimation. So you need to draw an initial set of samples before you have reached the stationary distribution from which you're wanting to draw. And so you want to throw away the initial samples. And every LDA package is going to have some default for the burn-in period, like 500 samples or 1,000 samples. But ideally, you'd want to sense check this. So you could compute the log likelihood of the data at each point in the Markov chain and start drawing samples when the log likelihood is stabilized. And that may or may not be at the point that the Python package has defaulted to. Okay. All I'm saying is, if you want to use these methods, you may not care about Bayesian approximation, but that will affect the quality of your estimates and your downstream analysis. Okay, so it cannot be completely avoided, and at least it can't be completely avoided if you want to do serious empirical research. Okay. Now, there's kind of an awkwardness. I'm trying to do 5 topics, but we only have 4 tutorial sessions. So I told Yabra to not cover topic models in the tutorial, right? So at some point, there is going to be a notebook on LDA where some of these modeling choices can be discussed. For the sake of getting to material that Yabra will cover in today's tutorial, I don't think I'll go through that tutorial in class today. But depending on how far we get, I may go through it tomorrow morning. Okay, so we can look at some of these choices from from the perspective of an actual applied problem. Right. All right. One more thing that came up in the break that's worth mentioning is this gentleman in the back, I guess Pascal, asked about how do I evaluate topic models. I forgot that one other common way is to look for sets of betas that sort of partition the vocabulary space. So in other words, the top words in one topic don't have high probabilities in other topics. There's some technical term for that in this literature. I can't quite remember what it is, but it's about sort of, in a sense, it's related to this anchor word idea that I want each beta to sort of occupy a distinct part of the vocabulary space. And you can evaluate the extent to which that's true by looking at the posterior probabilities in terms of topics. Yeah.
When you talk about top words, is it the same number of words for every topic? Because I guess, for example, in these 2 clouds, the loading is very different in the sense that the right one has a high loading on just 2 words, whereas the left one is a bit more evenly distributed. Yeah, so
I'm not a complete expert on this. I think it's typically statistics reported in terms of the top 20 words and maximizing like the extent to which that probability. So the 20 highest probability words here are low probability in all the other topics. But you're right, the top 20 might encompass only 1% of the total probability, or it might encompass 90% of the total probability. So you could define a similar statistic based on, I'm just going to go down the list until I've accounted for 20% of the probability in the multinomial. Okay. All right, so what am I meant to do with this? It's sort of fun to stare at these word clouds and stare at these theta distributions, but in the end, this is not doing research. This is doing exploratory descriptive analysis. What am I going to actually do with this? So most papers follow the research strategy of, so let me hide these controls again. Click back. All right, so I'm going to follow this strategy. I have a set of documents. I view LDA as some kind of data production tool, right? So I'm going to throw my document term matrix in, and out comes theta 1 ... theta d from my Python package. Theta d is now essentially data, right? And then I am going to perhaps take a particular element of these thetas. So I might take theta 1, k. Sorry, theta 1k to theta dk. Let's say if I've tried to identify there's a topic on China, right? And I go estimate earnings calls. I get a topic on China. And then I basically have a firm quarter database on how much we're talking about China. And then I go, use that to explore some finance question on supply chain risk during COVID, right? I'm just making something up. All right, so I basically have an upstream data generation technology with some validation, perhaps some thinking about model selection. But then those theta Ds get plugged into some downstream econometric model where a standard applied micro happens. So somebody asked me advice on publishing work in this area. As I don't know to what extent my own personal experience is idiosyncratic. Almost all referee comments I've gotten on papers that estimate topic models are in this space here, right? So they're questions about identification and the downstream econometric model, or all the typical stuff like, why did you run a particular difference in differences specification, whatever. Very few people ask questions about this upstream model as long as you convince them that the output is somehow reasonable. Okay. If you submit it to an econometrics journal, that might not be true. I'm talking about if you submit to a general interest journal asking an applied question, you typically get applied referees that talk about two. Okay. For example, if I can mention one paper I wrote, this FOMC data set that we've been staring at the outputs of was used in downstream econometric model to study the research question, how does the transparency of an institution affect how people interact with each other in that institution? So there's an old literature in contract theory on career concerns that predicts the existence of both herding and anti-herding behavior following an increase in transparency. So it's kind of an empirical question, whether or not when people are watched, they tend to talk like each other or want to start differentiating themselves from each other. So how could you implement this in an empirical strategy? Well, it turns out that in 1993, there was an exogenous publication of the FOMC transcripts that we've been analyzing in the slides so far. So they were in existence from the mid-1970s to 1993, but no one knew they were in existence for some strange bureaucratic reasons. Then in 1993, the whole backward batch was released, and those transcripts have been released with a 5-year lag going forward. So that's like a clean natural experiment that increases transparency. Well, from an applied micro perspective, that's not enough because other things happened in 1993. The Taylor rule was published in 1993, which might have also affected how monetary policy was discussed. So you can do a difference in differences analysis, where the second difference is taken with respect to a proxy for people's career concerns, which in this case was the amount of experience they had accumulated on the FOMC, because your career concerns are meant to decline in your experience, right? So that yields a difference in differences strategy in which you can assess to what extent the increase in transparency in 1993 differentially affected the people for whom career concerns should be more relevant. Why am I saying all of this? Not to talk about my work. That all of, the whole story that I just told you is just classic applied micro. Okay, and that is the discussion that was had in referee reports and whatnot. All this topic stuff was kind of upstream of all of that, and not, okay, it's sort of cool, but it's not the core of what's being done. Okay, I think that there's a little bit of a problem with that. All right, so I don't know if this is Stephen Hanson's personal obsession. I get the feeling it currently is, and it might always stay my personal obsession. But there's a kind of schizophrenia about that process, because the model that I just wrote down, the factor model we specified, LDA, does not admit any ex-ante heterogeneity in documents, right? The technical term for this is that all documents are exchangeable. They're generated from the same prior distribution. That's almost never what we're assuming about the data, right? So we're almost always assuming that there is a difference ex-ante in documents, like before and after transparency. But we're never kind of letting the upstream and the downstream parts of the empirical analysis interact with each other. Okay, so that's one problem. There's some sort of structural assumptions made in the econometric model that are inconsistent with the structural assumptions made in the upstream measurement. The second problem is that these things aren't data points, right? These things are posterior means. And if you plug them into a downstream regression model without accounting for their uncertainty, you're not getting correct standard errors. That has not stopped everyone from just ignoring all of this and proceeding as if this is data and I'm just going to pretend that none of this exists, okay? One of the reasons it's complicated, so you could model these two parts jointly. That's kind of a hassle. So you have to derive new Bayesian inference algorithms. Luckily, you don't have to do that anymore. If I have time at the end of the slides, I'll give you some ideas about how you might want to start jointly modeling these things. Now, I just want to point out that there's a tension in this empirical research that's sort of unexplored. Okay. A second problem is the lack of identification, which we've already discussed. Okay, so these thetas, if you take a frequentist perspective, are not unique. And so if you use a non-negative matrix factorization and you took whatever specific thetas were extracted from that as data, there's a problem because there's other equivalent representations of the data with different thetas. And to the extent that those different representations augment or shrink the heterogeneity, that of course is going to impact whatever hypothesis test you conduct in a econometric model. Okay, and again, this is not really discussed. So I want to go through one example of how these thetas have been used in a downstream empirical application. The reason I'm going through it is because it's a simple forecasting model, right? Not that I necessarily view it as the best in the literature, but it's kind of simple and easy to explain, and I think lets us build intuitions about why text might be useful in applied settings. So I'm going to be talking about conflict forecasting, but there are other papers in the macro literature that do macro forecasting with these topic models, right? And then there's many. I mean, if you go to IDEAS or RePEC and search latent Dirichlet allocation, by now there's probably hundreds of applications. Okay, so this is highly selected and somewhat arbitrary. So this is a paper by my ex-Barcelona colleague, Hannes Müller. That's another arbitrariness that I know Hannes and I know this paper and I think it's sort of cool. So that's one reason I'm discussing it. Which uses media articles to predict conflict. So why do we care about predicting conflict? Well, one is if you're a policymaker, it's useful to understand where you should be allocating resources, like military resources, for example. But if you're designing insurance contracts, like if you're a finance professor and you care about measuring risk and whether risk is being correctly priced, it's important to know where conflict is going to happen. So my sister actually used to work for Aon's defense underwriting team, and they care a lot about in which part of the world is a war going to start tomorrow, because it affects how they need to price their contracts for this stuff, all right? So the underlying text data is 700,000 articles during a, sometimes I struggle with basic math. I think that's a 40-year period, okay? Yeah, 40-year period. And there are 185 countries. So I was giving you an extraction of this data set in the example from 10 slides ago. So we chose the Iraq, Iran, and Syria articles. that's a subset of this full archive that covers 185 countries. Okay? So media data is a little bit harder to obtain than I would like it to be. There are basically two options. One is to go purchase an archive of media articles. So I purchased this Wall Street Journal corpus. I think they charge like $10K a year. Or luckily, a lot of universities subscribe to services that let you manually download articles. Okay, so this is from LexisNexis. Imperial subscribed to Factiva, which is a Dow Jones company. And in principle, you can scrape Factiva, but they don't like it, right? So in this case, I think Hannes and Christopher actually hired an RA for 3 months to just manually download 100 articles at a time from LexisNexis for 3 months, all right? Because if they catch you scraping the website, I think they cancel the license, at least temporarily, for the entire university, not just for you, right? So you need to be a little bit careful about this. All right, so what's the underlying data that needs to, oh, yeah?
Yeah, just a pragmatic question. So is it legal though to like web scrape? Because technically it's public information. I know that they can stop you from doing it, but like, is there any legal issues if we want to do this that we should be aware of?
That's a good, so I can tell you one story. I'm sorry, this is not it's kind of, I don't know. I'm being like a politician and not answering your question, but hopefully it's somehow related. So there's these guys in Norway wanted to do macro forecasting. And they're at the Norges Bank, the central bank of Norway. And there's like a Norwegian version of the Financial Times, which they started scraping. So it's like a public thing. And they hadn't set up sophisticated systems to keep people from scraping. So they just, downloaded the whole thing, estimated a topic model, extracted the thetas, used those as regressors in a structural VAR, and started producing like a Norwegian growth series that seemed to be a pretty good nowcast. And only when they started publishing that nowcast did the media company get in touch with them and say, what are you doing, guys? Like, you can't take my data, bulk downloading my data and then building a product from it and putting it online without our approval is not okay. So only at that point was there any legal issue. And up to that point, there was, it was not obvious from the web page that anything they were doing was not okay. And it was only kind of brought to their attention after the fact. Now that's Norway. I don't know what legal system they have and how it differs from the Spanish legal system or the UK legal system. So I guess the long and short of the story is, I guess one should proceed with caution about these things, even in cases where data is seemingly open. Who owns the IP and what exactly can be done with it is not something I'm totally clear on. So I thought I would get around the Factiva. Do you know what Selenium is? If you want, so the old way of scraping is to directly access the HTML of a web page, bulk download it, parse it, and extract what you want. Selenium is a Python package that lets you automate the keystrokes that you would need to manually do this. Yeah, you sort of pretend to be a human, and you can jitter it so that sometimes it takes you 7 seconds to drag the mouse, and sometimes it takes you 3 seconds to drag the mouse to the point where you have to manually download. And I hired an RA who's pretty good at this, but even then we got an email a month later from Dow Jones saying you need to stop bulk downloading our data at whatever regularity you're doing it. Okay, so I think the anti-scraping technologies and the licensed products that universities have bought are pretty sophisticated about these things. Okay, and if you want to buy Factiva, it's expensive, so it's like $50K per year for 200 sources or something. So one has to have a pretty serious research budget for it. All right, back to the point. The underlying outcome data that we're trying to predict here is conflict. Now, I hadn't realized that the definition of a conflict is, I guess, broad enough to define what we might think of as low-level conflicts. So there's something called the Uppsala Conflict Data Program, which collects data. So this is a panel data set covering these 185 countries at yearly frequency. And a country is defined to be in conflict if there were at least 25 battle-related deaths in the country in year T. Okay, so this is not like massive wars like in Ukraine or Iraq. This would also encompass low-level conflicts in the UK even, okay? So in some years in the 1970s and 1980s, more than 25 people died in this Catholic Protestant tension in Northern Ireland. All right, so it's not as sparse an outcome variable as you might think. Now, the traditional way of forecasting conflict in the literature, and apparently the CIA has invested lots and lots of money in this, and there are gurus who claim to be able to predict where a war is going to happen, takes the following form. So I want to predict whether there's a conflict in country I in year T. I'm going to regress that on country fixed effects and a set of covariates that's meant to capture whether a country is sort of ex ante likely to be in war. So you can use institutions, income shocks, rainfall shocks. So there's a kind of econometric literature on this that motivates why rainfall might lead to tensions over resources and so on. So you're basically going to pack a bunch of country covariates there. You're going to fit this simple model. So the reason I'm going through this model rather than the others is I don't want to have to specify a structural VAR here, which is more complicated. There's just a very simple linear panel data regression. All right, so I'm going to fit this object. I'm going to get regression coefficients for the alphas and the betas, and that's going to let me form a point estimate for the probability a country enters conflict in the year after my sample ends. All right, and that's gonna, you know, I can binarize that outcome, and if it's above 0.5, I'm going to predict a 1. If it's below 0.5, I'm going to predict a 0. Okay, so I've built a simple linear classifier. I'm not sure, do you know what a ROC curve is? Receiver operating characteristic curve. It's a way of assessing the classification performance of a binary classifier. I see a few nods, so that's good. So I actually sometimes don't know what this is. So I think the x-axis is the false positive rate, and the y-axis is the true positive rate. All right, so the best ROC curve is going to go to 1 immediately and just stay at 1. Okay, so that means I can achieve a perfect true classification rate and get no misclassifications. Okay, if I just do a random coin toss, so every time I need to classify something 0, 1, I'm just going to flip a coin, I would be at the 45-degree line, right? Because I would have an even chance of misclassifying something incorrectly classified. So ROC curves are sort of, you know, always lie in this upper quadrant of this space. So the interesting point of these ROC curves, and one is being generated for different sources of these X covariates, is that almost all of the predictive power of these models that have been financed by the CIA for, I don't know, 30 or 40 years is coming from the country fixed effects. If you drop the country fixed effects from these models and just rely on the covariates, you get the red curves, which are generally on the 45-degree line. Okay, and why is it not appealing to have a predictive model that only relies on country fixed effects? Well, you don't really need to pay someone $1 million to say, all right, the country that's going to be in conflict next year is Ukraine. Yeah, okay, I kind of knew that, all right? What I want to know is whether a country that has not historically been in conflict next year is going to be in conflict next year, okay? And if there's no history of conflict in a particular country, the fixed effect is going to be low, and so you'll get a correspondingly low probability that that country would ever enter conflict in the year after, okay? So enter text data. All right, so there's this upstream model that takes these media articles, transforms them into theta Ds. Those theta Ds get fed into this downstream predictive model as a full vector. So no stand is taken on extracting particular subcomponents. I'm going to put the full k-dimensional thetas into this model and recompare a model. So I'm replacing traditional numeric covariates with these thetas. And then I've got a model with country fixed effects and without country fixed effects. So the interesting thing is the within model produces nearly as good forecasts as the overall model. Right? So there's something that's happening within countries when you look at the media coverage in the New York Times that is able to capture when a country enters conflict in a way above and beyond its historical pattern. So let's go back to Ukraine, which is fresh in our minds. Now, maybe it's not the best example because I think in some ways there's been a war in Ukraine since 2014. And I think more than 25 people have died in every year since 2014. But what wasn't happening was a large-scale invasion. But if you read the New York Times, in late 2021, the US administration made a big point that there was about to be a full-scale invasion. They basically came and announced Russia will invade Ukraine in the coming months. Well, that was reported in the New York Times, right? And so if you had that data, you would be measuring those war words associated with Ukraine happening already in late 2021, which would have turned out to be a good predictor of a full-scale invasion in 2022, right? So the other cool thing is that you can, in any particular year, you can look at the ranking of countries based on which countries are most likely to enter conflict. And they pull out a few examples of situations in which countries with no prior history of conflict have very high predicted probability of entering conflict in future years. So one example is Yemen, and another example is Syria and Libya, which tipped into major conflicts in about 10 years ago. And this model is able to capture that. All right, so those are the ROC curves for predicting civil war and armed conflict, both with the country fixed effects in blue and without the country fixed effects in red. Okay, the point being, there is within country time series variation and topic coverage that's useful for this forecasting model. Right? So I hope you find this easy to digest example of why such data could be useful. If you're interested in more economics applications, I've put these papers here. But the idea is exactly the same. There's a big industry in macro forecasting for predicting quantitative data, controlling for other quantitative data. So there's the Stock and Watson paper, right, from, the late 90s or early 2000s for predicting inflation as a function of a high dimensional set of other macro time series. So one empirical exercise would be, to take a Financial Times, convert it into data through a topic model and include those as additional regressors in these large-scale macro forecasting models. The only innovation is that you basically have a new data source. You don't have a new statistical model of the time series relationships, okay? Just like here, it's the same forecasting model. We're just replacing X with theta. Now, if what you care about is uncertainty quantification, right? I want uncertainty around my forecasts, which is something that I think we should also care about. I think the issue that this is data is problematic, right? Because you're going to understate the uncertainty in any forecast you make, because there's also uncertainty in the thetas themselves, which should be reflected in the uncertainty in the point estimates from the forecasts. So it would not be correct to use the standard errors from these things as a measure of uncertainty for these. Of course, people still do it, but they shouldn't.
Bootstrap.
So one low-cost way of doing this without writing the joint model would be to bootstrap, but
Do you need to bootstrap from the corpus or exercise again and again?
Yeah, exactly. So that's one, like resample the document SUR matrix. Yeah, you can do that. All right, so let's change tack a little bit. This is meant to be about text and other unstructured data. Let me convince you that the investment that we just made in talking about factor models for discrete data has more general utility. Let's talk about survey data, which is also a very common kind of data in economics. We talked about the time use data from the Executive Time Use Project as a big document SUR matrix. So let's discuss ways in which I can analyze survey data using the same technology. All right, so survey data is arguably neither unstructured nor happenstance. Okay? But on the other hand, it is high dimensional and discrete. But the way we represent surveys in economics is often fairly rudimentary. So the Michigan Consumer Confidence Survey is an important headline macro number that's released every month. Do you know what the number is, where it comes from? I think that there are about 10 or 12 questions that a few thousand households are asked, and they rank things like 1 to 5, and an average is taken over their answers and released. And that's one of the, I don't know, 5 most important macro releases that happen in a given month. Well, who's to say that the underlying heterogeneity in consumer sentiment is equally reflected in all 12 of these questions? I bet many people in this room can't even tell me what the 12 questions are. Okay, so some might be more relevant for capturing heterogeneity than others, and so they may need to get higher weight in any sentiment index, but they don't. They're just averaged. Okay, so one motivation for writing down a proper latent variable model of survey data is to try to capture the sources of the relevant heterogeneity in a population, which is an important, measurement question. All right, so why would a latent variable model make sense for survey data? Let me give you 3 examples. So going back to this, example about sentiment about the economy, survey questions designed to measure sentiment, either at the household or the firm level, might ask questions like, do you believe that the stock market will be lower next year? Do you believe that business investment is falling or not? Presumably, there's a latent variable that you as an econometrician or empirical researcher care about measuring called consumer sentiment. And that consumer sentiment is going to generate some correlation in your answers to these 2 questions. Just like the underlying topic you're talking about in text is going to generate correlation in term counts. Okay, so one survey that I've analyzed is the survey for professional forecasters. All right, which is released by the Philadelphia Fed every quarter, I believe. And it asks, 20, 30 questions. And all of the questions are related to correlated objects in the economy. And the way you would extract an individual forecaster's sentiment should account for all of the sources of information in these 25 questions. In the end, I don't know if you know the Corbion-Gordonachenko paper from, 2013's AER, where they use the SPF to measure the frictions in people's belief formations. So they do an enormous macro literature on information frictions. I think they just take 1 question from the SPF out of the 50. Okay, so obviously there's a lot being ignored in belief formation by looking at this one, particular object. All right, so let's take politics. If you're socially conservative and you're answering some social survey, presumably your answers to a question like abortion is wrong and religion is important in public life are also going to be correlated, right? There's a big literature on management practices in firms where they go ask firms, 20, 30 questions about different HR practices. And the whole literature is meant to be about measuring a latent variable called management quality, basically. And so if you ask firms whether they conduct performance reviews or have inventory management systems, both of which are meant to be part of running an efficient organization, if you're higher on this latent dimension of being a more well-managed firm, there's going to be a correlation in answering those 2 questions too. So all I'm saying is there's many empirical settings where we have survey data that's composed of multiple questions, often more than a dozen. And what we really care about measuring is a latent object. And given that setup, we can apply a lot of the same machinery that we have for text. Yeah?
Are there papers that combine, say, the categorical data with those survey questions that people actually write stuff? Because sometimes, okay, you mark, I don't know, I believe business investment is falling. Sometimes they ask you why, then you can create from this corpus of answers something to add on what.
Yeah, that's right. I was thinking about that question this morning. Stephanie Stancheva had a paper that came out a few months ago where she took the free text responses to surveys and started saying, oh, look, this can be also considered data, even though it's typically ignored. And she talked about topic models and word embeddings and all the things we're going to talk about. But really, the same machinery for modeling all that text that she was pointing out can also be used to model the survey questions themselves. And it's not very difficult to imagine a joint model, right? Where there's a latent variable that's going to generate text that's also correlated with survey responses. And you can use both sources of information to infer what it is you really care about. I've never seen it done, But hopefully after we go through these slides, you'll see it's not that difficult. It's just specifying a joint data generating process. Okay. Oh, yeah.
Now, why not just principal components if you had like a 1 to 5 on all these questions?
I mean, I guess the same answer would be the one. So one answer is it's not the right model for the discrete data, in the same sense that it wasn't the right model for the document term matrix. So there's a paper, I reference it here, by Monroe and Ung, in the JBES, Journal of Business Economic Statistics. So they have, so I think the World Bank uses principal components analysis to represent some famous survey of poverty and income. And I can't remember the argument. I think it imposes some like linear combination on the survey responses that is somehow inappropriate. Like it takes you out of the range of 1 to 5 and then somehow it gets recompressed or something. I'm speaking in very vague terms because I don't have very precise understanding. But
something about the orthogonality conditions?
Yeah. So maybe I'll just take a look at an early version of this paper and come find you. And I mean, the generic answer is PCA is not appropriate for this kind of data, and it's gonna assume implicitly it's a multivariate Gaussian when it's not. But there's a deeper, I guess, answer about the kinds of representations that are given to survey data, which we really shouldn't view as admissible in this context that these guys emphasize. All right, so if we want to build this joint, this joint process for text and surveys, we sort of need to write down a data generating process for surveys. So there's something called the Bayesian grade of membership model, which is essentially exactly LDA with minor variance for survey data. So let me spend a couple slides describing it to you. And hopefully you'll find its structure familiar given what we've done before. So let's imagine that there are J survey questions. Okay, so it might be 20 survey questions. And every question J has a set of possible responses, right? And that might vary according to the question. So some questions might be yes, no. Some questions might be rank me on a 5-point scale. The important thing is that those are categorical responses, but most surveys are categorical. Okay. Now these responses don't need to have an ordinal interpretation, right? So answers 1, 2, 3 don't need to correspond to any ordinal scale. It's, what's your favorite color, red, blue, or yellow? Then 1 would be red, 2 would be blue, 3 would be yellow. So there's nothing special about 1, 2, 3 here. It's just a placeholder for the order of the question in the survey. Okay? Now we're gonna again assume that there are capital K, deep latent dimensions that I want my model to capture. And I'm going to assume that every latent profile generates a probability distribution over survey responses. Right? The only difference between this and regular LDA is that I'm going to have a separate distribution for each question. Right? So now I'm going to have every topic K induces a separate distribution over every question J. And the probability of observing the rth response in question J is given by this element of that beta vector. Okay. And an important assumption is that responses are going to be independent across questions given type. Okay, so if I'm a pessimistic type, I'm now taking independent draws across observations. Okay, so that's kind of, may be controversial, but that's, imposed in this model. We're going to put a Dirichlet prior distribution on these beta KJs, just as we did in LDA. Okay, so that's these, how do latent types induce distributions over survey responses? How am I going to model individual heterogeneity? Well, suppose that I observe, in separate respondents to the survey. So these would be the participants in the Michigan household survey, for example. I am going to collect my data, not in a document term matrix, but in a survey participant answer matrix. So for every person I'm going to record their response to the jth question. Right? So that's going to lie in the integers 1 to LJ. And then I'm going to have a person-specific theta distribution, also drawn from a Dirichlet, where the kth component of that person's theta represents their tendency to use that particular latent profile in generating their survey responses. The likelihood function is this. The only difference being I now have to factor over all of the questions in the survey rather than all of the vocabulary terms in a document term matrix. The inference issues are the same as an LDA. So there's a Gibbs sampler for inferring the betas and the thetas that looks very similar to the one that infers the betas and thetas in LDA. And let's look at an example. So I can try to convince you that this machinery delivers some value beyond just headline, let's take averages over survey responses. Yeah.
Yeah. Before doing this sort of estimation, you have to make some assumption of how many separate response profiles you have. Or do you determine?
Well, you have to do the same thing in LDA, right?
Yeah, but do you determine in a data-driven way, or you choose them as prior and then use this?
Well, the answer is so this Monroe-Ung paper, which I mentioned earlier, I think they use the information criteria. So this Arasheva paper, I think this is in the Annals of Applied Statistics. It introduces this Bayesian grade of membership model, and I think she proposes an AIC-like method for choosing K. So there's some issues because I can't come up with the likelihood of the model directly. I need to sample it. So there's a few issues around AICs, applications in sampled data rather than likelihood maximization directly, but the spirit is the same. Some trade-off between goodness of fit and model complexity. All right, so here's an application of this machinery. I've looked for economics applications. I haven't found any, but hopefully this course inspires somebody to go develop some of these for this joint model, which I think is kind of cool. So this is a survey data from something called the American National Election Survey that was conducted on election day in 1982. So there are 19 separate questions that people were asked. So I think the structure of the survey is you go to a polling station to vote, and then when you exit the polling station, a political scientist is there asking you your beliefs about things, okay? So there are 19 questions that are loosely grouped into your feelings about equal opportunity, economic individualism, and free enterprise. And for each of the 19 questions, you could either agree, can't decide, or disagree. And I'm about to show you the 19 questions on the next slide. So these researchers imposed k = 3 as the latent dimension. But in political data, at least in the US context, we might imagine there just being 2 dimensions, right? There's a kind of a left-right dimension, and I'm trying to locate each person on this left-right dimension. So in fact, it turns out that even though they've allowed for 3 types in the estimation, 2 types dominate the probability. And so the next slide only shows responses for 2 of these profiles. So there we go. These are the estimates of this Bayesian graded membership model. And I want you to think about this in terms of, say, inferring somebody's political beliefs and whether or not treating every question as equally informative is the right thing to do, right? All right, so just to be clear, what are we organizing here? So the first type is this k = 1. That's going to induce a probability distribution over saying that you agree to each of the 19 questions. So the first question is, do you believe in equal treatment? Okay, before the law, I guess. All right, so if you are a type 1 person, and this is unlabeled data, okay? So we're not imposing any external structure. It's still unsupervised learning. If you're a type 1 person, your probability of saying that you agree with equal treatment is 0.61. If you're a type 2 person, your probability of agreeing with equal treatment is 0.92, right? And then there's a probability of disagreement, right? But let's just focus on the agreement. These things don't exactly add to 1 because remember, they've dropped a 3rd type that doesn't occupy much probability mass. And there's another category of don't know that's also being excluded here, right? So I'm just focusing on the probability distributions over agree. All right, well, if you go down this k equals 1 response probability profiles and k equals 2 response probability profiles, I think that you can work out whether or not this is an interpretable latent dimension of heterogeneity on a left-right dimension. Okay, so which type is going to be the conservative type versus the liberal type? You see that from looking at this?
K1.
Yeah, K1 is what? The conservative, right? Exactly. So the conservative type is less likely to believe in equal treatment, more likely to believe in natural inequality, less likely to think inequality is a big problem, and so on and so on. Now, what I want you to focus on is that, you know, if you were to do like a Bayesian update on, like, let's think about the Ginskow-Shapiro-Taddy paper, but in survey space rather than term space. The Bayesian updates that you would form on somebody's latent classification are going to be very different across questions. So if I give you an answer to the question, you know, do you agree with democracy? There's not very much information contained in that response because both types are relatively likely to agree with democracy as a general principle. On the other hand, if I give you an answer to the question, inequality is a big problem, there's going to be a lot of differentiation. That's going to be informative for separating these types. Now, if I want to produce an aggregate index from these 19 survey responses on somebody's conservatism versus liberalism, the underlying algorithm is going to weight responses to all 19 of these things to come up with a theta. Okay? But there's going to be different sources of information across these 19 questions and delivering you that theta. Just as in the consumer confidence survey at the, you know, in Michigan, there may be some questions that are more informative than others. And I don't see anyone doing this in survey data and economics. I'll come back with you about this PCA thing because I think it's a good question. So it sort of suggests somebody is interested, at least the World Bank is interested in, you know, generating some aggregate output that combines a bunch of underlying questions, but they're not doing it within a, you know, well-founded statistical model, but it could be done. All right, so if you want to follow up with applications in economics, there are two that I'm aware of. So Mirko Draka and Carlo Schwartz, so Mirko's in Warwick, I think Carlo is in Bocconi, take something called the World Values Survey and estimate a latent type model and discover that in addition to the traditional left-right distinction that one observes in survey data, there's sort of a third type that seems anti-everything. Okay, so they interpret this as a populist type that sort of preceded the growth of populism as a political movement in the last 5 to 10 years. Okay, so the World Values Survey, I think, goes in waves every 5 years. And already in the year 2000, you could see, particularly in the US and the UK, that there was a latent type that started to answer survey questions that suggested they just didn't trust anybody anymore. Not so much that they were left-wing or right-wing. I've already mentioned this Monroe-Ung paper a few times. They actually do take this consumer survey from Michigan, estimate a basically Bayesian graded membership model, and show something interesting. The heterogeneity in these survey responses, and using this AIC, they have a k equals 4, I believe. So it does track sentiment. So there's some latent dimension that tracks sentiment, but there's also other dimensions that track uncertainty in addition to the real economy. The point being, there's more information in this household survey than is traditionally reported in macro data. All right, so I was told by Stefano I need to finish now, so it's yeah.
Anonymous responses here would be treated as another category?
Yeah, exactly. Yeah, so they could just be missing. That's augmenting the response set. So it's quite a flexible machinery.